So in today's lecture, we'll start first by discussing the Gaussian distribution. So this is the most popularly known and most used PDF, and it's given as the Gaussian distribution is symmetric about mu, and sigma is a measure of its width. This distribution is primarily named after Gauss, the mathematician, but it has been discovered and investigated by many people independently. The French usually name it after Laplace, who had noted its main properties when Gauss was just a toddler. And in fact, the first known reference to it before even Laplace was born is by the Englishman de Moivre in 1733, who did not realize the importance of this distribution and did not make any further use of it. And its specific importance in probability and statistics came only after Gauss. So let's look at some of its properties. The mean is simply mu. Similarly, the variance is nothing but the square of sigma square, which appears as a parameter in the distribution. The skewness as well as kurtosis are both 0. And as we have remarked earlier, this is a symmetric distribution about the mean. Now if you look at the central moments, then for odd n, this comes out to be 0, whereas for even n, so get this double factorial times sigma to the power n, but this can also be written as n factorial by n by 2 factorial and 2 to the power n by 2 multiplied by sigma to the power n, sigma being the standard deviation. And lastly, the characteristic function phi of t is given as the exponential of it mu minus half t square sigma square. Sometimes while using the Gaussian, it is convenient to shift the origin so from x to x prime equals x minus mu, which allows us to write, it basically makes the mean 0. The distribution becomes 1 by 2 pi sigma square e to the power minus x prime square by 2 sigma square. We can even change the scale. So we can scale it as from x to z, where z is defined as x minus mu by sigma, which allows us to define a standard variable, that is a variable with mu equals 0 and sigma equals 1, which basically gives us what is known as the unit Gaussian or the unit normal or the standard normal PDF. And this is simply expressed as, so this distribution has this random variable z, mean 0 and standard deviation 1, and we can write it as 1 by square root of 2 pi e to the power minus z square by 2. And its cumulative distribution function can be identified as the error function. Is the integral from minus infinity to some z of e to the power minus x square by 2. So this is known as the error function, or alternatively the normal probability integral. Now if on the other hand we are working with the Gaussian distribution, not the unit Gaussian, then for n x mu sigma square, the CDF is given by the error function of x minus mu by sigma. Now the Gaussian can be shown to be a limiting case of nearly all commonly used probability distribution functions. And this is a consequence of the central limit theorem, something we will discuss shortly. And we can state the following relations among the various distributions we have discussed so far. So let's say the multinomial and we have the binomial, we have the Poisson, and we have the Gaussian. So the multinomial is characterized by a vector of random variables k, the probabilities and the number of trials. The binomial, we have a single random variable k with the parameters n and p. Poisson is described by the random variable k and its mean mu. And lastly, we have Gaussian. It's characterized by both the mean and the standard deviation. So in the case of the multinomial, k and p have dimension m. So if we take the limit of m equal to 2, Then from the multinomial we get to the binomial. Similarly, take the limit of p tending to 0, but np equal to mu as constant, then that takes us from the binomial to the Poisson. Now, as far as the Gaussian is concerned, both from the multinomial and the binomial, Gaussian can be arrived by taking the n going to infinity limit, where n is the number of trials done. Whereas from the Poisson, we can reach the Gaussian by taking mu going to infinity limit. So next, let's come to the reproductive property. We have seen that the Poisson PDF has this property. Gaussian is a limit of the Poisson. So therefore, Gaussian is also reproductive. Now it can be treated as an exercise to show that if x and y are random variables, independent random variables, are distributed according to the Gaussian distributions nx mu x sigma x square and ny mu y sigma y square. Then z equals x plus y is also Gaussian distributed with nz mu z and sigma z square, where mu z is mu x plus mu y and sigma z square is sigma x square plus sigma y square. Having discussed the Gaussian or the normal distribution, we can, as a next step, discuss its generalizations. So the first one that we'll consider is, it's known as log normal distribution. So now if a random variable y is normally distributed with mean mu and variance sigma square, then the random variable x, where x equals e to the power y, is distributed as this factor of 1 by x on the outside comes because of the Jacobian. So if you remember the relation between the new PDF and the old PDF after transformation of variables, then in the case of continuous PDFs, there was always a factor of the Jacobian. Now the properties in this case, the mean turns out to be exponential of mu plus half sigma square, and the variance is given as exponential of 2 mu plus sigma square, exponential of sigma square minus 1. Now it must be noted, for the log normal distribution, mu and sigma square, these are not the mean and variance for this PDF. Even though these are the parameters in terms of which the mean and variance of the log normal distribution is computed. The next generalization is the multivariate Gaussian or normal distribution. So now let us consider n random variables xi with means mu I. So we'll write them using the vector notation. The Gaussian is an exponential of a quadratic form in x minus mu. So when we want to generalize the Gaussian to more than one dimension, we replace x minus mu by the most n-dimensional quadratic form symmetric about the point mu. Now this quadratic form is where A is an n cross n matrix. Now, since this has been constructed to be symmetric about mu, we must have the expectation for this entire vector x should be the vector mu. Or in other words, expectation of x minus mu should be 0. So this can be written explicitly as an integral from minus infinity to plus infinity. We rewrite the distribution here. This is the quantity that we want to vanish. So if we differentiate this with respect to mu, so what we get is the following. So here 1 refers to the identity matrix. So this can be rewritten in terms of expectation, because we are multiplying something with the probability density function. And we are taking the integral from minus infinity to plus infinity. So this is nothing but the expectation of identity minus x minus mu times x minus mu transpose times A and this should be 0. Or since 1 is just a constant, the identity is just a constant, we'll take it to the other side and we can write it as E x minus mu transpose. I can take in the constant A outside. This is the identity. But this expectation is nothing but the definition of the covariance matrix. So we denote by V. So this relation basically says that V times A should be identity, or in other words, A is nothing but the inverse of the covariant matrix. Now, if the correlations between all xi are 0, that is, if rho ij equals to 0 for I not equal to j, then V is a diagonal matrix with sigma 1 square, sigma 2 square, sigma n square on the diagonals. That would imply that A is also diagonal with just the reciprocal of those same diagonal entries. And then we can write exponential of minus half minus mu transpose times A times x minus mu is nothing but the exponential minus half times x1 minus mu1 square by sigma 1 square plus x2 minus mu2 square by sigma 2 square and so on. Or in other words, we can split out the exponential of the sum as the product of exponentials. Cxp minus x1 minus mu1 square by 2 sigma 1 square times exponential of minus x2 minus mu2 square by 2 sigma 2 square and so on. So this probability density function is just the product of n one-dimensional Gaussians. So all rho ij, where I is not equal to j, implies that xi and xj are independent. Again, a word of caution. This observation is true for this particular PDF. As we have seen before, this is not true for all PDFs. The last step that remains is to obtain the normalization, and with the normalization, the result that we get is is 2 pi to the power n by 2 appears. So the root 2 pi factor appears for each of the exponentials, each of the Gaussians. And additionally, we get the determinant of v. Basically comes out as a product of the eigenvalues. And this is based on the assumption that V is non-singular. That is, determinant of V is not equal to 0. If V is singular, and that would imply 2 of the xi are completely correlated. Which basically mean mod of rho ij equals 1. And in such a case, we can replace xj by some function of xi, therefore reducing the dimension by 1. So the special case of the multivariate Gaussian or multivariate normal is the binormal or bivariate normal PDF. So this is the multivariate normal PDF for 2 dimensions. So here we can write the covariance matrix as sigma x square, sigma y square, and on the off diagonal we have rho sigma x, sigma y, rho sigma x, sigma y, which basically tells us that the inverse will have this form 1 by sigma x square, sigma y square, 1 minus rho square, sigma y square, and the distribution function is given as f of x comma y. We have this 2 pi sigma x sigma y square root of 1 minus rho square, and the exponential of minus half g, where this g is actually written as one by 1 minus rho square times x minus mu x by sigma x squared. It's 2 rho x minus mu x sigma x y minus mu y sigma y plus y minus mu y by sigma y square. Now we get contours of constant probability density by setting the exponent equal to a constant. And these are called covariance ellipses. Let's say if we look at g equals 1, you can get an ellipse with extreme values at mu x plus minus sigma x, mu y plus minus sigma y. So let's make a schematic drawing of this for better illustration. So then this, we can draw an ellipse, something like this. And this is at some angle theta. on the extreme points. Basically, the larger the correlation, the thinner is the ellipse. It approaches 0 as mod phi goes to 1. Mod of rho goes to 1. Now, of course, in the limit, so as rho equals plus or minus 1, G is infinite. And we really have just one dimension. So the orientation of the major axis of the ellipse is given by tan 2 theta, which can be computed as 2 rho sigma x sigma y by sigma x square minus sigma y square. If so, theta is 45 degrees if and only if sigma x square equals sigma y square, and theta is 0 only if rho is 0. Now, for the one-dimensional case, the one-dimensional Gaussian, the probability that x is within k standard deviations of mu, which you can write as p of mu minus k sigma is then equal to x is then equal to mu plus k sigma, is given by an integral like this. So this is an integral over the interval where g is less than or equal to k. In 2 dimensions, so the 2D generalization is the probability that the point x comma y is within the ellipse corresponding to k standard deviations. And this is given by P of g less than or equal to k equals 1 by 2 pi sigma x sigma y 1 minus rho square, and the integral is over this g less than or equal to k 1 minus g by 2 dx dy. Of course, doing the integral analytically is not as straightforward, so for further discussion we'll refer to some table of values. So let's say for different k, we have k equals 1, 2, 3, 4, 5, 6. First we'll look at p for g less than or equal to k. which is the 2D case. And we can also look at the one-dimensional case, P mu minus k sigma less than equal to x less than equal to mu plus k sigma. So this is my one-dimensional case. And the last one would be product of two 1D distributions. So you look at the numbers, they take values like this. It's quite clear that the two-dimensional probability for a given k is much less than the corresponding 1D probability, and even less than the product of two 1D probabilities. This can be seen based on the fact that the product of two 1D probabilities basically mark a rectangular region. So something like this. Whereas for the 2D probability, what we have is basically an ellipse. Clearly, since the ellipse has a smaller area than the rectangle, the probability of being within the ellipse is less than the probability of being within the rectangle. Since the covariance matrix is symmetric, there exists a unitary transformation which diagonalizes it. So in 2 dimensions, this is a rotation matrix. Which will denote by U as simply cos theta minus sin theta, cos theta. Now this matrix transforms our coordinates as well. It takes x comma y to, let's say, u comma v. Well, we can write it as a matrix multiplication and the new covariance matrix that will be given as U V U transpose. Since the transformation is unitary, areas are preserved. It is unitary transformation implies that mod of j equals 1. So therefore, the probability that x comma y lies inside the ellipse is equal to the probability that u comma v lies inside the ellipse. The standard deviations of u and v are found from the transformed covariance matrix, and after some algebra, these can be shown to have the following forms. Or alternatively, you can also write these as So if we start from the uncorrelated, the diagonalized variables, a rotation by theta to the new variables would allow us to write sigma x square equals sigma u square cos square theta plus sigma v square sin square theta, sigma y square sigma v square cos square theta plus sigma u square sin square theta. And the covariance correlation coefficient is just sin theta cos theta times sigma u square minus sigma v square by sigma x sigma y. Now if rho is fairly large, that is if the ellipse is thin, just knowing sigma x and sigma y would give a wrong impression of how close a point x comma y is to the mean mu x mu y. The properties for the marginal distributions and the conditional distributions of the multivariate normal PDF can be extended to the bivariate case as well, and the marginal PDF comes out to be simply the Gaussian in one variable. And the conditional PDF, say f of y given x, which is the joint PDF of x and y, divided by the marginal PDF of x. This quantity can be written as 1 by 2 pi sigma y square, so 1 minus rho square, the exponential of minus 1 by 2 sigma y square, 1 minus rho square, and this multiplied by y minus mu y plus rho sigma y by sigma x, x minus mu x, and we put a square on this whole thing. Or in other words, this is a Gaussian with a random variable y, and mean given as mu y plus rho sigma y by sigma x, x minus mu x, and the variance given as sigma y square times 1 minus rho square.